This is actually a collaboration between people who are wireless networking people and some experts in optimization. So Hanif Sherali is actually an industrial engineer, and he's very, very well known in this area of optimization. So they joined forces to look at these problems. But it's not hard to imagine that these things get very complex very fast, and that you cannot always rely on classical optimization techniques to try to find the solution. So sometimes you have to apply some heuristics. I'll talk a little bit about the heuristics in a moment. Let me also mention that there is a variant where instead of doing classical optimization in a very centralized way, so if you imagine a base station that if it could, it would try to solve this problem and then assign spectrum to everyone. So some genie-like creature that is trying to assign everything and knows everything about the network, etc. Sometimes you are actually interested in the distributed problem. So you're still trying to achieve some optimization objective, but you're trying to achieve that in a distributed way, where there is no centralized genie making decisions, but all of the components of the network, and these components can be the actual radios in the network, or the components can be base stations throughout the network. It doesn't matter, but it's multiple components that are trying to achieve the same goal, but they do need to do that in a distributed way. So distributed optimization is one optimization problem where each variable and constraint is owned by a different agent within the network. So if we imagine n agents that want to cooperatively find a vector x, so that's an m-dimensional vector that minimizes the sum of these functions f sub I of x, where each of these functions, each of these f sub i's, is known only to one of the agents in the network. So these are functions from the m-dimensional vector x into the real numbers. So you're ultimately trying to minimize some scalar value. But each of these functions is known by a different agent, and they are trying to optimize a common objective. So they may have to exchange some information. They may do it a little bit by trial and error, where they change something and then they see what the effect is on the overall objective function, and then they try something else, and so on. So it's quite a bit more complicated than having a centralized optimization problem, but that's what the circumstance is. That's what the actual resource management problem that the network faces is. Okay. So distributed optimization we see sometimes applied to cognitive networking problems. What you see even more often is the use of game theory. And I could talk all day about game theory, but I promise that I will not. So I just wanted to mention it very briefly because it is widely used. How many people have worked with game theory here? No one.
I have, yes.
Yeah. Just a few people here. How many people have heard of game theory? Okay, very good. Somewhere in between, like Nash equilibrium. Okay, fine. So, all right.
Beautiful Mind, maybe.
Have you seen the Beautiful Mind movie? Yeah, it's that's all you need to know about game theory.
Plus, that the Nobel Prize talk was fake at the moment.
Well, yeah. There's huge debate about Nobel Prize, so don't even get me started.
No.
Whether that's a fake Nobel Prize or not, the economic.
His talk dedicated to his wife
Oh,
was fake in the movie.
yeah. Many things that the movie doesn't cover, but the book is very good. The book is very excellent, and it's told me lots of things about John Nash that I found quite useful, and I use all the time with my students. So I have to tell this story, and let's see if I can afford the time. Probably not, but I'll tell it anyway. So apparently, John Nash was a professor of mathematics at Princeton, and of course, genius, huge contributions to game theory. But when you work in the mathematics department as a professor, you usually take turns teaching the lower level courses that are not very popular among professors to teach because they're often service courses that are taught to all kinds of students and large classes. So apparently every once in a while, John Nash had to teach Calculus 1 to these large classes. So anyway, he would teach Calculus 1 every so often, and has the reputation of being a terrible professor, just terrible teacher, because he would work, his mind works at a very fast rate, so very difficult for the students to follow. But then when it came to the final exam, he would give these final exams to students, and the final exam was always prove this theorem that no one had been able to prove yet. So some conjecture that mathematicians thought were true, but that none of them had been able to prove. Sometimes having nothing to do with calculus. So it could be like Fermat's last theorem or something like that, some prime number related thing. And so none of the students obviously did very well on the final. But his philosophy, John Nash's philosophy, was that mathematicians had been working for sometimes centuries to solve these problems. But these freshman students, first-year students, were coming fresh at the problem with a fresh mind. So during the exam, maybe they would have, the intuition that eluded all of the mathematicians. So I don't think it ever worked, but I tell my students, okay, it doesn't matter how tough my exam is, it's not one of John Nash's exams. So I'm not going to give you a problem, to solve that I have no idea what the solution is. So by comparison, in that respect, by comparison, I think I'm a better professor than John Nash. But I still would much rather have him teach me game theory, on the other hand. So anyway, so game theory models conflict and cooperation among rational players. So in problems where there's autonomy, so it's a resource management problem where different entities, and again, you can think about radios, or like mobile radios, or you can think about base stations being the entities. Doesn't matter. It's just the entities have autonomy in the decisions that they make. You can think about the networks being the entities if they are trying to achieve some sharing of spectrum, for instance. So it's a very good match for the idea of game theory, because you have rational decision makers. They may be the cognitive radios, they may be the cognitive networks, whatever, that are trying to achieve some goal and to do that in an autonomous way. So you set a game consisting of multiple players, sometimes the players are the radios themselves, a set of actions for each player. So the action could be, for instance, what the transmit power is, or what frequency I select, or what bandwidth I use for transmission. And then there is, this is a very complicated way of saying something very simple. There's some set of utilities. So there's one utility for each user, each player, that's trying to maximize. So again, it's an optimization problem, but it's not only a distributed optimization problem, but one where the different agents, the different players, are trying to maximize different things. So it's no longer just this distributed optimization problem where everyone was trying to distributedly maximize the same function. So it's difficult because as they are trying to maximize the same function, they don't know exactly what their impact is on this optimization objective. But it's different from game theory, where you're trying to maximize your own optimization function, and my optimization function is different from yours. And therefore, there's a more inherent conflict potential in the problem. There are actually two flavors of game theory. There's what's called cooperative game theory and non-cooperative game theory. These ideas are often misunderstood by people who are starting to use game theory in their work, because people have the tendency to say cooperative means the person is being really nasty and evil. And non-cooperative means that. And cooperative means the person is being really nice and wants to really kind of work together. But that's not what it means in game theory at all. So non-cooperative just means that the players, the entities, are making their decisions independently without any sort of coordination. And cooperative means that the entities can actually enter into agreements. So they can bargain with each other, they can enter into contracts, etc. So it's not that they are nice in one case and not nice in the other case. There's no moral judgment for these things. These things are rages, first of all. They don't have morals, or they're not people. So, so there's no moral value in cooperative or non-cooperative game theory. Non-cooperative just means autonomous entities making decisions independently. Cooperative means autonomous entities also trying to maximize their own objectives, but who can enter into agreements with one another. And you see lots and lots of papers on game theory in resource management and cognitive rages. Some of the early papers were done by Joe DiNio, who did his PhD a number of years ago on the use of game theory for cognitive rages. So he actually got to get some of the low-hanging fruit there because he was one of the first people looking at that. So, for instance, this paper from 2004, so pretty old in terms of cognitive rage, is looking at a power control game, very simple power control game. The game is made up of a set of players, which are the users, the rages in this case, a set of actions, which is the transmit power level for each user, so that's the action of each user, and a set of utility functions, which is basically a signal to noise and interference ratio type of utility function. So each radio I belonging to N sets its transmit power P sub I to maximize some utility function. Notice that the utility function is a function of the vector P, the vector of all of the transmit powers of all of the N radios. And that is an important aspect of a game theoretic formulation, because if my utility is just dependent on my own action, that's just a simple optimization problem. I just find what's the optimum P sub I that maximizes my own utility. The problem, what makes this as a game theoretic problem, is that my utility depends on everyone's selection of a power level. And because what the transmit power that you choose affects, of course, the level of interference that I experience. So the utility function that he has is simply the signal to interference and noise ratio. So the numerator is the received power at the desired receiver, and the denominator is the sum of noise and interference. And then you set this up as a game and try to find out what the outcome would be. So what would be the predicted power levels for all of the end users? What do you think is going to happen in a game like this?
Selfish behavior. Sort of a selfish behavior.
Selfish behavior, yes. It's always kind of selfish anyway, because I want to maximize my own utility, right? So I don't really care about anyone else's utility. I'm not trying to maximize the sum of utilities or anything like that. So yes, selfish, but what would you expect from this selfish behavior? So what's going to happen?
To be unstable?
No, it's actually stable in terms of there's an equilibrium in this case. So in terms of stability, there's a point of equilibrium that these rages will reach. But it's not going to be a very good equilibrium, because what will often happen in a situation like this is that I increase my power level. I have an incentive to increase my power level because that's going to increase my utility by increasing the numerator. But that will decrease your utility, leading you to have to increase your power level, and you end up with this. Yeah, so you end up with this shouting match, or this kind of war type of thing where I build more weapons, then you have to build more weapons to defend against my weapons, and I have to build more weapons. And so it's just keeps going, and everyone, if you constrain the power, if you say, okay, these radios can only transmit between 0 and some P max, you may end up with an equilibrium where everyone's transmitting at P max. So you have to start thinking in terms of radio resource management, what incentives do you embed here to actually lead to a more rational, no, I don't want to say rational because this is perfectly rational, but a more efficient outcome. Okay, so one of my PhD students, so several years ago, looked at the use of cooperative game theory in a very, very similar problem. So also a problem of trying to share the existing resources among autonomous entities, so autonomous radios. And this, what Juan looked into was the sharing of spectrum. So you have a large band that you can split into subbands, and a set of users need to select, each radio needs to select the subbands, how many subbands and which subbands that it wants to occupy. And again, it's going to try to maximize some utility, which is the sum over all the subbands that it selects for itself of some capacity type of expression. The only difference is that Juan used cooperative game theory. Well, there are other differences, but the one main difference that Juan used cooperative game theory to look at this example. So it means that the users can bargain with each other to try to achieve a good division of the spectrum. And then he looked at some different concepts of solutions under cooperative game theory. There are different ways. Nash studied some cooperative game theory, but others also did, and they have different solutions to this problem, what are called bargaining solutions. There's something called the Nash bargaining solution. There's something called the Calais-Moroditsky bargaining solution, etc. So we looked at this problem from a cooperative game theory point of view. What can be called cognitive and what cannot be called cognitive is one that generates infinite amount of discussion, so I have my own ideas about it, and if I need to summarize, it's the following. First of all, some of my early students and I used to have these conversations, and at some point I said, I don't